Hello, everyone. This is our, I think, second in-person Heidelberg AI event this year. It's so cool to see so many of you come here, even though the sun is shining outside, even though there's a machine learning conference right now happening also in Heidelberg, taking us our visitors. But we have a great speaker here, so it will be totally worth it. And as always, after the talk, you're welcome to stay here for more drinks, and we also ordered pizza, so we can have like some snacks and socialize and talk about machine learning. So, all right, so without further ado, I'm gonna introduce our speaker, Niki. So he studied physics in Regensburg and then went to do a PhD in Tübingen with Bernhard Schulkopf and also in Cambridge. And he just told us about that he also did two internships there. One sounded very fun, not so much work, but lots of. So at Google they have 100 different rooms with like band practices or meditation room or all these things. So apparently you can have a lot of fun there. And then he now got a position in Munich at Helmholtz Munich and leads a group there, also at Helmholtz AI, which is the platform that's supposed to support all the Helmholtz centers in Germany with AI. And as you know, DKFZ is also a Helmholtz center. And yeah, he's also a professor at Technical University of Munich. And yeah, so far he's been researching on causality a lot and also in between a little bit of fairness, but today we heard that fairness is kind of over. Maybe he can elaborate on that. And today he's gonna go back to the roots of physics, of his, the circle is closing back to your physics past, and he's gonna talk about how to learn dynamical laws from data. So please welcome Niki.
Thanks for the introduction. I'm going to start right away. Am I supposed to say something? This is yours, yeah. Okay.
Oh, I forgot something, sorry. Yeah, so I just, this is brought to you by the Medical Image Computing division of DKFZ and my junior group for interactive machine learning, organizing this together. And also we have lots of partners here in Heidelberg, the Alice unit, and also the data science seminar led by Lena Meyer-Hein. And yeah, all of us together organize these kind of events and seminar series. And it's growing to be a really nice ecosystem of AI here in Heidelberg as a nice location for this research field. Sorry, now let's go.
Thanks again, totally worth it. Okay, I'm going to talk about learning dynamical laws from data, and please interrupt me at any time if you have any questions. So I want to start with the motivation for doing this, and I guess usually it's understood that this may be an interesting task. I want to motivate it slightly differently. I'm coming at this from thinking about causality, as Paul just told us. And there's this famous table that you find in some textbooks and also other places where they write out what you can do with different types of modeling levels, so to speak. So on the bottom here would be statistical modeling, which is kind of boring, right? There's lots of no's. The pointer is can't really see it. Maybe I can show it here. Yeah. So you can't really predict under changing distributions or answer counterfactual questions. Then as you go up, causal graphical models are doing a bit better, and then structural causal models are also quite interesting, and this is what we tend to study in causality. But then the table has this extra row, which would be mechanistic or physical systems. And when seeing this, I thought, okay, well, when this one ticks all the boxes, then maybe we should aim at this one, right? It seems maybe both can be learned from data, so why would I bother with structural causal models? In a recent talk by Bernhard, actually, so also my ex-PhD advisor, this would be great if we could learn this from data. And he's shown this table, so I took a picture. And now he suddenly says that differential equation models cannot be learned from data, so he puts a no there. So I want to challenge that, and let's see if we can still do something there. Okay, so the setting is relatively easy. It would be, I paraphrase this as a dream of an automated scientist that goes out, looks at a system, either looks at the stars or looks at a microscopic system, does a bunch of thinking just after looking at it, and then comes up with the governing equations. In sort of less visual terms, this would translate to having observed a trajectory, right, x of t, maybe here it's 4 different variables, and you would then want to go to this f that governs the differential equation. So here the dot would be the temporal derivative, and this is a standard ODE. And we want to go just from observations to this f. Can we learn the governing equation? And that begs tons of questions, right? Like, what do we observe exactly? I'll say a few words about on the next slide. And also, what do we assume about the underlying dynamics, right? Surely we have to say something about the f we want to find. And these can be super high-level things. Are we interested in ODEs or PDEs or other types of differential equations? Or do we assume that they're in canonical form? Right here, I've written x dot as a function, like it is a function of just x and t. You could also say, well, the x dot can also be an argument, right? It's not as explicit, it's just implicitly in there. Is it about scalar, multivariate equations, linear, nonlinear? Do we assume something about them being autonomous? So does the t enter explicitly in this function, or is it only the x, and so on? And to make some restrictions already for this talk, and then we will look at different pockets, I will focus on ODEs in canonical form, so the way they are written here. Some time derivative equals a function of x and t at this point. Okay, then to the other point, so that was about the thing we want to learn. We have sort of restricted the output space of what we want to do. And what about the input space? The most informative setting is where you have a full trajectory, right? That would mean the full continuous function, which you can't even have on a computer in that sense, right? At least not in terms of observations. So the first thing that probably happens in practice is that you only get discretized observations. Maybe they are not regularly sampled. Maybe they're also noisy. Maybe you only have partial observations, right? Like maybe the system really has 7 variables, these extra lines I'm showing here, and you're only observing 4 of them. Can you still learn the function? Maybe you have actually more information by observing multiple trajectories from the same system. That should help rather than hurt you. And there's also an interesting question that comes up once you think about chaotic systems, namely whether you're observing long or short horizons. Right here, we are seeing a chaotic system over the first 2 seconds. So it looks like just a trajectory doing something. But when you integrate this for longer, then it becomes this well-known Lorentz attractor. And you see that the trajectory actually traces out continuously this manifold. So here it makes a difference of whether you only observe sort of this incoming transient that goes in first, or whether you have mapped out the full thing. And I guess it should be intuitive that when you have observed more of this trajectory, it should be easier to learn the dynamics. And there could be many other things here. Okay, so before we dive into all these complications, I guess one thing I've learned in causality that people talk about identifiability all the time, and no one really knows what we mean often. It's a bit fuzzy. But that's the first thing that comes to mind. Is this even something we should expect to be able to solve, right? Can we do this in principle? And before we tackle the question, a few preliminaries. I've already talked about this differentiation between non-autonomous or autonomous equations and higher or order equations or first order equations. So here I just want to reduce our work a little bit. And when we look at a non-autonomous system of equations, so non-autonomous here means that t is an extra argument. Often that's used to incorporate a driving term, right? Some external force that shakes the system. And we have a d-dimensional system sort of variables evolving. Then we can always do this mathematical trick or just redefinition. We can say our new coordinates are x tilde, which contain all the variables, and add t as a variable of the system. And then you get a new differential equation where now the temporal derivative of this joint thing is just what you had before, right? So the first entry, which is d-dimensional, would just be your function. And then the temporal derivative of t is just 1. So now you have a new differential equation, which is autonomous, right? On the right-hand side, there is no t explicitly as an extra argument anymore. So that allows us to, at least on paper, write non-autonomous systems as just 1 dimension higher autonomous systems, so we sort of don't bother with non-autonomous ones. And you can do the same thing for higher order systems. So let's say you have this third order differential equation. Now, f could, in principle, also depend on x dot and x dot dot. For simplicity, I only keep the x here. Then again, you can write up a new variable that consists of x, x dot dot. So all the derivatives up to the one that is the highest one. That is the order of the ODE. And then you can write an ODE in set. So set dot, just add one dot above all the variables that we defined here. And then you can see that, well, the second one is just the third entry of our state variable. And the, am I getting this right? Yeah. X dot is the second entry, x dot dot is the third entry, so these are the first two. And then x triple dot is just given by the original function as a function of set 1. Okay, so all this is just to say that, again, we have reduced sort of a higher order system to a first order ODE in higher dimensions, in k times d dimensions, if k is the order and d is the original dimensionality. All I'm saying here is that we will focus on first order autonomous systems, and that's not really a restriction when it comes to higher order and non-autonomous ones. And there's lots of subtleties in this, right? When you actually want to do this from data and you only observe the state for a third order system, then you're suddenly missing initial conditions that you haven't observed, you would have to estimate. So it's not all that easy, but we're in principle, can we even solve this task? So let's focus on this. Okay, what is identifiability? The question is, let's say I start with an ODE and it produces this solution trajectory. Then the system f, the ODE is identifiable if there is no other f prime that would have also given rise to this trajectory, right? So we're looking at the inverse task. We're not doing the usual thing where you solve the ODE forward and get the trajectory, but we want to go from the trajectory backwards. And the problem comes up when there is another f prime that is different from f, such that both of them have this trajectory as a solution. Then it would be non-identifiable. Okay, yeah. So it's the sort of the inverse problem, in a sense, that could be underspecified, if you want to say it in other terms. And the initial conditions, of course, have to be the same, otherwise the trajectories couldn't agree. But still, you could have different f's that give rise to the same trajectory for this initial condition. And this already gives rise to multiple types of identifiability. You could answer things like, for this given initial condition, is there a different f? Or when for the given f, I pick any initial condition, is for all of them, for all of them, does there exist another f prime such that they have the same trajectory for some of them, and so on. So there's also subtleties in how you want to define identifiability. And this is sort of the rough outline of what they all looks like. If we have a trajectory, can we identify f? And before we make this more precise, I want to do a quick excursion. I'm not sure if this is interesting to anyone, but some of you may have thought about this. Sounds a lot like things we do in control, and there is close ties to control theory. So if we look at this version of what a typical control problem looks like, is that you have this additional input to the function, which is a control that you can control. Like you get to choose it externally. You can probe the system in different ways. And another feature that typically comes up in control is that you have some observation function. So you're not observing the full state of the system, but you're only observing part of it, a transformation of parts of it, and so on. This is captured by the function g. So then y would be what you observe, x would be the unobserved state, and f would be the dynamics. And then also in fields like system identification, you would want to learn about f. Often this y is sort of lower dimensional than the full state. And they have other questions around identification, and they're closely connected with the ideas of controllability of a system. Do you get to steer it to any state you want? And observability of a system. Do the observations suffice to infer the full state? So questions they have is that if is a fixed f identifiable when we control u? So you get to probe the system multiple times with different inputs, which should help you in identifying f. Or for a given parametric model class of f, so let's say you have fixed what f can generally look like, but there are still some parameters that are unknown, is a subspace of that class identifiable? Like, can you say it's within that range of parameters and so on? So there's many related questions that people in control have been asking for a long time, and admittedly, we're still learning and figuring out about these connections as well. Okay, in our setting, we say there's no control. Think of an astronomical system. I don't get to shake the stars. We're really just passive observers. This also goes with the tradition of causality, where mostly we assume we only have observational data, and then we want to learn something more deeply about the underlying system. And by the way, so we don't get to control it, and we say we have full observations, right? We want to start simple. And a little add-on on control, if you started this very common linear control problem, then you can make it our problem by saying that the use that you get to pick, the controls, are just delta controls, so they are just delta peaks at the beginning, and you can choose them such that they correspond to a given initial condition. So sort of every initial delta peak control would set the initial condition, and then you're sort of back to our problem, right? You just have the ODE and an initial condition, and then you want to identify F. So this is sort of the correlation here. And again, if you have full observation of the state, or a rank n C matrix, which means essentially as much as you have observed the state fully, because you can invert it and get the state back. Okay, so people have found out about 10 years ago, this was in the Stanhope paper, that this model is identifiable first the definition. They call this identifiable in a given subspace of matrices. Right here, the space of ODEs is essentially the different matrices A you can have here. That's all there is to specify about your F. It's just the matrix A. And it is identifiable in a subspace of these matrices if for all A and B in the space that are different, there exists an initial condition that you can plug in such that you get different trajectories. So can think about this a bit. That there's quite a few choices you could make. You could say, for a given A, is there another B? Or do you pick all pairs at once and say for each one of them you want to be able to distinguish them? So it's not immediately clear how you want to define identifiability. But this is their definition, which is relatively strong. So it says for each pair, you need to be able to distinguish them by some initial condition. And they show that it is identifiable. So any two different systems, you will find at least one trajectory where they're different. This is quite nice. So in the linear case, it seems like identifiability is not completely out of scope. All right, now I want to go to a general definition, the one that we'll be working with in this talk for the most part, is we restrict ourselves to a class of allowed functions. Right? These are the ODEs we consider. On the previous slide, it was implicit that it's all the linear ones. Only A has to be specified. Here, it could be some class of functions. We have as input an observed trajectory. It's on a finite interval. We don't get to observe infinite times, but we have the full state trajectory. So that means X really is the full function, right? You have observations for every real value in 0 and t. It's not just discrete observations. Then we call the function f identifiable from X in F, right? There's two things going on from the observation and within the function class. If there's no other f prime such that X is also a solution to this function. So in pictures, this is the X that we are given. We set ourselves a space of function that is allowed. And we look at the initial conditions. We have the full trajectory, so we have the full initial conditions. And then we know there is one f that if you integrate it forward with this initial condition gives the trajectory. And we call it identifiable if there's no other f prime in the space such that for this initial condition you would get the trajectory. There could be another f prime outside the class you've specified, right? That's why the f is part of the definition. So you identify it within a hypothesis space if you want. So it's also apparent that one way to make identifiability easy is just to make this tilde f very small, right? Like we probably did with the linear systems. Then it's unlikely that within the small space you have another one. Okay, let's gain some intuition for when we should expect this to work. There's a bunch of choices I have on the left. Let's say we start, we still are in the setting where we have noise-free continuous inputs, so the trajectory of observed without noise and fully. And let's focus on scalar systems first, because we want to just gain some intuition. Then let's say this is the solution trajectory we have observed, and the question is, can you identify f? What you see here is that you really only trace out this one line, right? F is a function now of x and t and gives out a vector. So f really is a vector field, and I've drawn it in this picture. And now it becomes a bit more clear is if you only see the blue line, can you draw the entire vector field? And the answer is probably no, right? Like I could just flip a bunch of arrows in the top left corner here and leave all the other ones on the bottom intact. And you can see, well, there could be another f. You haven't even probed that region of space up there. So surely you can't just fully identify the f by only looking at this one line. Okay, so what we're looking for now, we can go, okay, let's go even simpler. Let's make it autonomous. So there is no t dimension, right? It seems I've been cheating here because I gave a sort of space in this 2D space where I changed something at a time earlier where x hasn't reached that space yet. So if we have the autonomous case, we only have this one. Then same problem, f is a function of x, right? So on the left is the trajectory over time. And then on the right, I'm showing f of x as a function of x. So the inputs that we get to f that we have seen in the trajectory only go from 0.7 to 0.95, right? This is the only space in which you've seen x. So it's this green shaded region is the vertical region that is traced out by the trajectory. So really, when looking only at the trajectory, you can only learn about f on the inputs it has received, right? Which is the space between 0.7 and 0.95. So clearly, again, you could have a different f that looks something like this, that agrees with the original f in the relevant region, and that's still different overall. Okay, so now that makes it very obvious, right? The question is, can we infer an entire function by only having probed it or sort of seen its output on a small interval? And this is just an extrapolation task, right? So really, when we ask for identification, in this best case, we can have scalar, autonomous, full, continuous inputs. We're sort of asking for extrapolation. So if we only probe it along the trajectory, it's like only seeing this part of the function, and then I ask you continue the function. Give me one unique correct way to continue the function. So clearly, this is generally impossible, but there is a few classes of functions that probably come to mind where this is easy, namely linear functions, right? If you see 2 points of a linear function, you're done. You can extrapolate it. Polynomials are a nice class. If you know it's at most degree k polynomial, you need k+1 observations, since they're all noise-free. And if you see the continuous one, then no matter how small the interval, there's exactly one polynomial that fits. And also, maybe a bit more obscure, or I wouldn't even call it obscure, but functions that are analytic, which means essentially that the Taylor series or some power series converges on an entire domain. And the power series you can compute locally, right? You only need a continuous little interval. Then you can compute all the derivatives at that point. And then if you have a power series that converges, then you're also done. And now, linear and polynomial classes of functions sound like a severe restriction. Analytic is less clear, right? Analytic functions are pretty rich. There's lots of functions in the class of analytic functions. But they really depend on you having continuous observations, right? As soon as you have discrete ones, you don't get to compute all the derivatives up to arbitrary order as soon as there's noise. So it seems like a theoretically interesting but practically irrelevant consideration here, that analytic functions are identifiable from a single solution trajectory. Okay, and then you may say, well, of course, I don't want to be able to extrapolate a function to infinite left and infinite right all the time. So maybe I only care about it on the domain I've seen, or a small extension. But then the whole point of it becomes a bit irrelevant, right? If you only want to learn f in this green region, well, yes, you can do that. But then as soon as I give you a new initial condition, or as soon as you want to continue this function, you don't even know what to do, right? It could be that the orange line outside the right half flattens out or keeps going down. So then it's essentially impractical to do any forecasting or any generalization with that model you're inferring. So we really do want to extrapolate. Okay, then let's dive a bit deeper. We've now seen the scalar linear case. This is fairly obvious. I'm going to do a quick, I think I need to watch time, so I'm going to do this relatively quickly. Reducing it further, linear systems, we make them homogeneous, get rid of the b, and we make them autonomous, get rid of the time. So x dot equals ax, but now it's not scalar anymore. Here, this is very well understood. We can just write out the solution analytically for each initial condition, and also it's well understood theoretically, even though really this has been done in 2014 to a large extent, but then really the full picture has only been fleshed out 2 years ago, which to me is insane, right? That we only understand identifiability of linear systems a couple years ago. So here, the statement is fairly simple. The system A is identifiable in the entire space of linear functions, right? As part of the definition from X, which is the input we get, if and only if it is not confined to a proper subspace. And the it refers to the trajectory. Sorry about that. So you can imagine, here you have a 4-dimensional space, and the trajectory wiggles around, and it needs to sort of explore all directions, which makes sense because as soon as you have 2 points in one direction, you get to draw the linear line, right? But if you don't even explore anything in this direction and you only stay in this plane, you won't be able to tell what's going on in the other one. Okay, easy enough. There you can do beautiful linear algebra, and again, surprising this hasn't been done earlier. And it also neatly extends to linear in parameter systems, meaning any systems that are not necessarily just a matrix times x, but a matrix times nonlinear transformations of x, of the individual components. So you could have, 5 times the sine of x1 plus 7 times the cosine of x2, like linear combinations of nonlinear functions of the components, which is, again, not a tiny class of functions. Okay, so then let's look at some examples. If A has repeated eigenvalues, then it's always unidentifiable. Repeated eigenvalues essentially translates to wherever you start, you will not explore one of the directions. So here, if we take A as this matrix with this initial condition, then B, a different matrix, will give you the exact same trajectory from this initial condition. But you have to choose the B sort of adaptively for the initial condition. So if you start at a different point, then it will be a different system that gives you the same initial condition. Okay, when A has no repeated eigenvalues, then there may still be a case where it is not identifiable, namely if X is contained in a proper invariant subspace. What's a proper invariant subspace? An invariant subspace is one that is left alone when A is applied to the entire subspace. So a subspace that is mapped onto itself by A, and proper just means that it's not the entire space. So again, it's reasonable that if you have a subspace where if you take a point in the subspace and you apply A, it ends up again in the subspace, then you never get to move outside. So when you now think of how the solution is sort of just the matrix exponential of A, then it's just repeated multiplications with A. So you're never going to leave that subspace. You're not exploring all directions. You won't be able to identify it. So visualization in 2 dimensions. This point here, when you shoot it off, it does span sort of the plane, right? You can identify it. But then there's these 2 red lines where when you start on this red line, you will always stay on this red line. And for these points, those are exactly the ones where you could have another system that gives the same solution. Here we have B. If we start at the same point for this matrix, we actually get the same trajectory. So from the blue trajectory, we can't distinguish between A and B. But from the orange one, we can. So here, it's, A is identifiable only from a trajectory that starts at the right point. And the right point here is everything except those 2 red lines. Okay, for some systems, wherever you start, it will always trace out both dimensions. It doesn't matter. And this scales to higher dimensions. Okay, so for this interesting linear autonomous case, if you have repeated eigenvalues of your system, you're doomed. If you don't have repeated eigenvalues, then you may still get unlucky if your initial condition is in one of those invariant subspaces. If that's the case, you're doomed. Otherwise, you're good. And now in these papers, especially in this more recent one, they make the argument that the matrices within all Rnn that do have repeated eigenvalues, they form a small set, right? So it's a set of 0 measure under the Lebesgue measure, which means as much as there's very few of them. If that doesn't say anything to you. And similarly, x0, the initial condition being in a proper invariant subspace, means that it's in actually a lower dimensional space than the full one. So again, it has 0 Lebesgue measure because it's lower dimensional. So all the paths that lead to doomed are very rare, if you wish. So they use this to essentially conclude that under mild assumptions about the distribution. And what I mean here is that you can do this in Lebesgue measure, but you could also set up some random matrix model. But most of them will have 0 mass on the repeated eigenvalue, most reasonable ones that have been studied. And that means that essentially linear autonomous homogeneous systems are identifiable for almost all trajectories. And the key point, of course, is that we're still talking about noise-free continuous observations. But that solves the linear case to a very large extent. One thing we're recently thinking about, okay, first there's extensions to the affine case, so you can add back the plus b. It changes things slightly. I would have thought it all goes through the same way, but it changes things very slightly. But overall, the message is still it's identifiable. And then people have studied what happens when you have noisy observations, discrete observations, but that really is just in the beginnings. So there's hardly any work on theoretical guarantees of identifiability when you have discrete observations, even for linear settings. And one thing we're also thinking about is what happens in sparse systems. So when I think of a high-dimensional biological system, for example, I don't expect every variable to be driven by all other variables, right? Often you have sparsity. The derivative of x5 only depends on x2, x7, and x9, for example. And suddenly, these arguments about the 0 Lebesgue measure don't quite work out. Once you have sparse matrices, it's much more likely for them to have repeated eigenvalues. And that means that when you restrict yourself to only sparse matrices, whatever that space should be like, right? You need to define some subspace of R n times n that consists of all the sparse matrices. Then it's not clear whether they still have zero Lebesgue measure or whether that's something that's going to happen very likely, that you have repeated eigenvalues and won't be able to identify the system. Yeah, we're currently thinking about that, not really making much progress, but it's very interesting. And even more recently, this is interesting since it's also happened by colleagues in Munich, and we've never talked still to this day, even though they have very similar interests apparently. It just shows how everyone's got enough to do on their own. They've also looked into the uniqueness problem of physical law learning, precisely starting from the definition that I've shown you. They do this fully for PDEs, so this is a very confusing table. It's extremely mathematical, but they sort of say that they really start the paper by saying, isn't it insane that people have been inferring dynamics from data for decades, and it seems nobody has thought about whether that even works as a problem. So I think it's a very, very forceful abstract and introduction. And then they really go through all large different classes of functions and check whether they are identifiable. And they do this in the PDE case, but ODEs are sort of a special case of that. So the results are pretty much in line. I think they were not aware of the linear casework. At least it's not cited in the paper, which is also interesting. So they redid the entire work, but it maps to the same outcome. And they say linear ones are identifiable under some linear independence conditions. So here, essentially, this G1 to GK being linearly independent is precisely the condition that your trajectory has to span, not be contained in a proper subspace. In the polynomial or algebraic case, they also come to the conclusion that it works if you sort of probe all directions, which is not as clear anymore. So here there's this condition on a Jacobi having full rank at some point, which also means at some point you have to be able to go in all directions roughly. And then they also have this analytic case as a special one, where they again say, analyticity really helps you in extrapolating, essentially. So it's the same 3 sets of functions that you would also naively come up with to check, because there is extrapolation. And then as soon as you go beyond that and you just say, C0 would be continuous functions, once differentiable, and so on, up to smooth functions, then what this thing here means is essentially that your trajectory would have to probe all of R. Right? So along your trajectory, you have to visit every single point in the entire space. Okay, sorry, there's, for them, K is what for me was the dimensionality. Okay, so this is very unlikely, right? You're not going to find a trajectory that spans all of our K in a continuous fashion. So essentially it means that as soon as you allow larger classes of functions, you're not identifiable. And that also sort of concludes this theoretical question. And this was only published earlier this year. And maybe to credit also what happened earlier, right? So I've been saying this, that we haven't really thought about this problem until recently. It's not quite true. I think traditionally, people have been interested in parameter inference when they learned dynamical systems. So the setting was more something like this. Again, you have your ODE, you have an initial condition, and also typically people have looked at cases where you have an observation function. And a classic scenario that inspired their problems was things like epidemics. So you may be familiar with this SIR model. It's modeling the number of susceptible people for a disease or illness, the infected people and the recovered people. And really, you're already giving this equation as the one that counts. So in a sense, for them, my curly f, the class of allowed functions, is precisely this equation, but the parameter values could vary. So when we say it hasn't really been studied, I think it's just that as a mathematician, when you talk about a function class, you think about linear, polynomial, analytic. For them, it was just different parameter values for a given structure of functions. And then here, it's a case where you only observe the infected ones, right? Those are the ones that show up. And you still want to infer something about the system, maybe the parameters or a combination of parameters or something like that from only this observation. So the observation often is sort of a selection where you only get to measure some things. So they're always in this partial observation case, which I haven't talked about yet at all. Right? So they're, in a sense, in a more difficult case. And then it's not so much for them about learning the entire F, but often they are just interested in the reproduction rate, right? A beta over gamma ratio, or just a beta, or something like this. So the questions are much more targeted to a specific system, to a specific parameter. And the way identifiability analysis for them works is that you want to just say, given that this is my function, that these two parameters are unknown, and this is what I observe, can I identify gamma? So there's much more input, much more focus, it's much more narrow. And then they have completely different techniques from the theoretical ones studied so far, where they then get to, okay, yeah, I'm not gonna, if you're interested in the different ways you can do identifiability analysis for a given system, then these are two good overviews. I recognize I only, you probably won't find the paper from just this. I can send out the list of the full references. Okay, so that's also to give credit to what people have done previously. So it's not really that we're just starting this identifiability question. And a little outside glimpse again on identifiability from a sort of different lens is when you have a chaotic system, then the trajectory itself is not really that much of interest, because you have this property that if you start from a slightly different initial condition, trajectories will diverge exponentially. So in any real setting, you're never gonna nail it down exactly. There's always noise in different ways. And the analogy that's often mentioned here is that weather forecasting would be trying to predict the trajectory exactly forward, right? That works as long as you do it for a short time span. As soon as you do it for a long time span, it may go off in a completely different way. And studying climate, or the changes of climate, is studying the properties of this entire structure here. So in a chaotic system, you have something that's called an invariant measure, or often the attractor, which is sort of the manifold that is traced out by this trajectory if you let it run infinitely. Then it actually densely traces out this manifold. And you can learn a lot about the governing dynamics by looking at the shape of the attractor. And then it doesn't matter so much what trajectory you're looking at exactly, because the name attractor already suggests it. Every trajectory that you start in a reasonable vicinity will go on that attractor ultimately and trace it out infinitely. So there's also a huge field of work that tries to study dynamical systems or infer dynamical systems from studying sort of this volume of the attractor, which is different from what we are doing here, where we really look at a trajectory. Okay, that was the identifiability theory part. So now, given that we know we can't do it, let's just try to do it and see what happens. And okay, here, maybe this should illustrate, now we're also interested in discrete data, there is noise on it, and sort of we just want to do it. Let's see what happens. And the naivest way you could try to do this, now that we're all machine learners, if we have such a system and there is an f and we want to learn the f, then just make it a neural network, right? Parameterize the function f. And now let's see where we go from there. We have our inputs, which is measurements of x along the trajectory, right? We have the first one, the second, the 0th, which would be the initial value that we observe, and then the trajectory continues. So if we now just have our neural network that is of this shape, so it takes in d-dimensional inputs, it gives out d-dimensional time derivatives. If we feed this in, what we should get is the derivative at the first time, right, at the 0th time step. And what can we do with that? When we have the derivative and we have the starting point, then we can take a step forward. So here, you could take an ODE solver, just take that derivative you got from the network and take a step. In the simplest way, you could do the simple Euler forward solver, where you just take the derivative that you get with your current network and multiply it by a small time step and take a step. Okay, the small time step should actually be the time difference between the two observations here. And then you get an estimate for x1, and now we are in a situation where we know what to do. We have a predicted x1, we have the measured x1, we take an MSE loss, we have a parameter of a neural network. All of this in here is differentiable, and we just go. We optimize. And to many of you, this may sound familiar. Okay. One last glimpse back to the theoretical identifiability part is, if we now wonder whether this is identifiable, we suddenly have to grapple with questions of what function class is represented by neural networks. And you may say, universal approximators, it's all smooth functions, so we're doomed, but then for a finite neural network, not really. Maybe these are all analytic. So yeah, these are interesting questions. But okay, what I've just described is, of course, just a neural ordinary differential equation. it's interesting how the way they developed it originally was by thinking of infinite depth neural networks, and there's always images in the latent space, and dynamics happen in latent space. And you're not really learning a given dynamic, but just some way of evolving the latent space so you can then do predictions on classification. So it's a very different motivation. But when you strip away all the complexity, then really it's just trying to learn a dynamic from observations. So that's quite nice. And one thing we did on top of that, so of course you can just do that and try to learn dynamics, and people have written papers on how neural ODEs work much better than many previous versions that people have devised to learn dynamics, even though I'm not sure that's the case. And what we thought is that, again, this idea of sparsity, right? Here you get this black box, densely connected neural network that connects every input to every output. So every gradient can be determined by every state. Coming from causality, again, there is this idea of autonomous, independent module sparsity everywhere. So that's the first thing that came to mind is, can we enforce sparsity on this? So really, when I have my state vectors and my derivatives, I want only x1 and x3 to go into x2 dot, and I want only x3 and x4 to go into x4 dot, and so on. Of course, I don't want to have to pre-specify that. I want to learn that, but I only want few inputs to affect few outputs. And we ended up in a domain that people have found interesting from, I guess, completely other dimensions, namely when you just want sparsity in neural networks, right? When you have a linear regression, you do lasso, and you have a neural network, what do you do? We just tried out the naivest thing we could cook up. We take the original neural ODE loss, which is just this MSE between the predicted values and the next observations. And then what you want to do is you want to regularize full input-output connections, right? You don't just want to regularize weights, because even if each weight layer is sparse, you may still have connections, paths going from each input to each output. So you want to simultaneously regularize all connections from input 1 to input 3, for example. And one way you can do that is to just look at the individual weight matrices in these layers. And when you multiply them all together, like this, like the last one, and then the middle ones to the first one, then in the entry, so of this entire product, the entry in the fourth row and the second column will have contained all paths you can go, right? The sum of all products of all the possible paths you can go through this network from the, I don't know what is that, the third input to the second output. And there's a little subtlety because you have these non-activations in between, these non-linear activation functions in between, which may mess you up, right? If you use a ReLU, then it zeroes out many things where it becomes a bit subtle. But we can show that if you just take the point element-wise absolute value of each of the weight layers, you multiply them all together, and then you say in this final matrix, I want to have many zeros, then this is an upper bound on the number of active input-output connections. So we may be regularizing too much. We may try to make it sparser than it needs to be, but then ultimately, this is just a tweaking problem anyway to tweak the regularization parameter. And also what's nice is that if you have no activation functions, so you're just representing a linear network. If you have no nonlinear activations, then all of this is just one big matrix multiply. Then this exactly becomes sparsity on the weight matrix. And then we've just tried this on some simulations, and what we're showing here is sort of the input-output connectivity matrix, right? Sort of how x goes into x dot. And because this is, in this case, it's linear systems, so each connection is literally just a number. And we tried, there's other ways where people have tried to get sparsity in neural networks. Group lasso is one famous one. And essentially, it seems to work pretty well to just regularize this product up to pretty high dimensions in the linear case. And then being surrounded by computational biologists, I'm slightly uncomfortable showing this slide, knowing nothing about what I'm showing here. But we looked at some gene regulatory network data. So essentially, we have single cell data, and we have some reason to believe that we have an idea of how cells develop over time. And then we measure a bunch of genes over that pseudo-time. It's not real time, but it's inferred pseudo-time. But we act as if genes followed an ODE over pseudo-time. Do with that what you want. But when we then just train this neural ODE with this regularizer on it, and we measure sort of the influence, we can extend this measure from influence to the nonlinear case as well. Then we see that essentially there's only two genes that really have an influence on the outputs, right? So expression levels and velocities, how much they change. And so I've been told that these GATA genes are ones that we supposed to be driver genes, that we assume to be driver genes that do actually infer changes. And when we looked at the trajectories of just the genes together, you wouldn't be able at all to tell that these two are the ones inducing the changes, because all the others seemed much more correlated among each other. It really seemed like those two are doing their own thing. So it was quite interesting and surprising and somewhat uneasing that it actually found those two, because data is extremely scarce, so there's a pile of salt to take with these results. Okay, and then we also extended this further. So I think this weight multiplication regularizer idea was quite expensive and not really only scalable in the linear case. So we found another way, a more principled way of knocking out entire input-output connections, where the idea is just to have sort of a concrete dropout regularizer that punishes full path connections from inputs to outputs simultaneously. And that worked much better. So the second paper, this research was mostly driven by Hanna and also Till at Helmholtz. And they really did an extensive analysis of now also sort of our previous method, the new one, and other existing methods. And also looked into how weight sparsity, sort of how many weights you can knock out fully, and feature sparsity correlate and correspond to each other. So if you're interested in this at all, then this is a good place to start. And with this PathReg method, we also tried more real-world examples. Here we have motion capture data. So what you record is X, Y, Z positions for a fixed number of joints in the body that was taken by motion capture. And if you just train a neural ODE on it and you give it this test data as input, so this is a trajectory that it hasn't seen during training, so it only learned the dynamics and then wants to predict from a new initial condition, and you let it forecast here, then the standard neural ODE quickly dissolves into weird-looking shapes, whereas if you do regularize for sparsity, it looks much more reasonable. So the idea is that sparsity also helps you in identifying the true dynamics because it acts as a regularizer. And I have no idea how to get that fact together with what I stated earlier, that sparsity may make identifiability much harder. We'll see. Okay, here you can then again look at these influence metrics, and here they're a bit harder because there's many joints, so there's 31 joints. And it's a second order equation, so the position and the velocity go into the acceleration, but still you get to see interesting blocks of correlation where the acceleration of the left and the right leg, so these are the joints that make up the left and the right leg, are mostly driven by the position and velocity of the left and the right leg in a walking motion. And then you can look at Y, X, and Z positions separately. It becomes hard to visualize whether that makes sense, but on a very high level, the correlations that were found do make sense. Not correlation, sort of the input-output dependencies. And then we looked through other things like walking and waving and golfing. And if you're interested in the details, again, you can check out whether all these patterns make sense physically. Okay, now I'm switching gears slightly. This was our first exploration in using sparsity to infer dynamics from data. And another one is constraints. So again, think of a standard neural ODE. If you learn your F perfectly and your system is sort of a closed orbit planetary motion, then this is what you would get, right? The star is the initial condition. If you learn it perfectly and you predict forward, then it will remain a closed orbit. As soon as your network is slightly off, which is gonna likely be the case, you may encounter situations like these, right? Where the star slowly spirals in. And you only see one trajectory that looks near perfect, sort of one period. But as you keep forecasting further into the future, this will be far off. And the idea is that here, really, the only thing we need is conservation of momentum to get this perfect, right? But the neural ODE doesn't know anything about that. So the quest is, can we tell the neural ODE something about prior knowledge that we have? And the way in which we formulate prior knowledge is in terms of a constraint on the trajectories. So here we say that trajectories have to be confined to this manifold, and the manifold is defined implicitly as some zero set of a function. So this is fairly general, right? For many manifolds, submanifolds of RD, you can find a function that defines it by the level set at 0. This, for example, works for all kinds of conservation laws. If you have holonomic constraints, meaning that, let's say you have a pendulum and you're recording XY coordinates, then you're sort of over-determining the system. And there's a constraint because x squared plus y squared has to be the length squared of the pendulum. So you can incorporate these kinds of things, because maybe you know, for the pendulum, it's clear, just record the angle, but in other systems, you may know these holonomic constraints and still don't know what better coordinates to choose, or your just measurement device hasn't measured them. And also constraints from control. So if you have a system, but you control it to do a certain thing, then that also acts as a constraint on the dynamics. And the whole idea of this is that if we go back to this example of this orbit that should be circular, and if the blue is now the true f, if you learn it slightly imperfectly, it may tilt inwards. So can we change the learned function to actually push it onto that manifold? Right? In this case, the manifold would exactly be the circle on which the trajectory should be confined. So we want to have the inner errors point slightly towards the circle and the outer ones also slightly towards the circle. So if you do happen to go off, you're pushed back onto the circle. And there's some old ideas in just stabilizing ODE solvers that we essentially repurposed here. And what we do is, instead of trying to learn the original neural ODE, we learn this one where we say x dot is f theta, so the original one. And then we add this extra term, gamma is just a parameter. And what we have here is the pseudo-inverse of the Jacobian times g of x, where g is the function of the manifold. So very roughly, to give intuition, is that if you take the Jacobian of the constraint manifold, it's a bit like the tangent space. And the pseudo-inverse of this Jacobian will project you back onto that space. So you check if x has left the manifold, then g of x will be non-zero, otherwise it is 0. And then you sort of project this back onto the manifold. Okay, that's the whole idea. You can show that this equation has the same solution as without this term. And you can also show that locally, within some epsilon, whatever, you will be pushed back onto the manifold if the trajectory leaves it. And then we run this for a bunch of systems, and this would be this two-body circling problem. This is the revolution of a rigid body. So here you have angular momentum, or essentially the Casimir function, if you've heard that, is essentially conservation of angular momentum in a rotating body. Here we have a DC-DC converter where there's some switching involved. So you're switching to transfer energy between two capacitors. And all I want you to see here is that if you train a standard neural ODE, it will have low error up to some time, and then it will just diverge and go off. Whereas if you do stabilize, so this SNDE is for stabilized neural differential equations, then the error will remain small, and also you control the conservation of the quantity. And here, these are not all conservation laws, but these can be other things, like here in a controlled robot arm. So here you have a robot arm with 3 joints, and we put a controller in place that makes the last one, so this one is fixed, and the last point here is sort of moved in a sine wave left and right. And that puts constraints on the dynamics of this arm. And again, the orange line traces out the black one, which is ground truth. So here the differences are more subtle. It's only after 100 seconds that the neural ODE really goes south. But then afterwards, the error really shoots up. Whereas if you stabilize it, you can control it. And we also studied one of these chaotic systems, a double pendulum that develops chaos. So it's very sensitive to the initial condition. And here it's not as clear, right? So neural ODE performs also quite well. Maybe we do a little bit better, especially in relative error after a long time span. So initially it's quite the same. Over a long time spans, we do still do better in error. But what's more interesting is that as I've said in the beginning, for chaotic systems, you're often more interested in recovering the attractor. And what we measure here is the Hellinger distance, right? So we use the learned ODE, and then we solve it forward for a long time. So we have really traced out this attractor. And then we measure the distance. And here the Hellinger distance is a common measure between sort of the points you get on the attractor from solving the learned ODE towards the ground truth one. And as we increase this gamma, our parameter, to stabilize, we're really getting much better in recovering this attractor. Okay, how am I doing time-wise? Not too good. But I think we started 10 minutes late, so I'll go for a bit more. Okay, now a completely different approach. We started from looking at a trajectory, trying to get an equation. So then you can have a different idea in saying, what if I start from many trajectories for which I know the equations? This now starts to look like a machine learning problem, right? You have lots of examples, input examples, and typically they come as sequences of points, right? You just have sequences of measurements. They may be noisy and irregular. And on the right-hand side, you have equations, if you know which equation corresponds to which solution trajectory. But those are also just sequences, right? You can encode them a bit nicer, write them in a different font, and then write them in infix or prefix expression. Then it really looks like a sequence of operators and symbols, right? There's a fixed set of operators, a fixed set of symbols, and it's some sequence thereof. Okay, now you just have a standard sequence-to-sequence task, and if we have infinite data, then we definitely know what to do, right? So we just employ the bitter lesson and throw lots of compute on it. So the question is, how do we get infinite amounts of data? And here it's very simple. We can just simulate all of this, right? You need to essentially get pairs between mathematical expressions and their solution trajectories. Once I have the expression, I just throw it into an ODE solver and I get the trajectory, right? That's no problem. So how do you sample mathematical expressions? And people have also come up in 2019 with smart ways of doing that. You just give it two trays of operators, binary operators that take two inputs, unary operators, the usual mathematical functions that you have, the basic functions, and you give it symbols. For us, again, sorry for the switch from x to y, so now y is the trajectory. You give it y dot, maybe t, and it can choose different constants. And then there is this nice tree sampling algorithm where you build a binary tree and then you sort of decorate the internal nodes randomly with binary or unary operators. And you can put in some constants, you can put in the symbols you have, and you sort of have to specify probability distributions over all of this, right? For every internal binary node of a random binary tree, which binary operator do I put on it? Which unary operator do I put on the ones that have only one child? And how do I distribute the symbols and the constants? But once you've fixed all of these choices, you have essentially written down a distribution over mathematical expressions. It's not very amenable, right? It's not easy to handle. It's not clear what expressions you have captured, but you have your distribution. And then you can just go ahead and sample as many mathematical expressions as you want. So you have an expression, then we sample an initial condition from some distribution. We put it into an ODE solver, we get the trajectory. So now we have the pair of the trajectory and the target, and now there's lots of trickery in making a transformer like this to take in. So you somehow have to encode these numeric sequence values into something the transformer can handle as an input. And here, one key aspect is that there's huge variations often in trajectories. When you have an exponential one, you may span orders of magnitudes. And if you just put them in as numerical values, then you run into numerical precision errors pretty quickly. And one thing that we have stolen from another paper is they literally just take the IEEE encoding as in a bitwise fashion, right? So if you have a double number, you just take out the sign, the mantissa, and the exponent things as 1-0 strings. And you can literally just feed in every float as a string of 1 zeros as it's represented in the IEEE format. And that gives you a nice sequence of only 2 tokens, 0 and 1. Okay, and then you feed that in as the input sequence, t and y, and if you have multiple components, y1, y2, and so on, then you may still add some noise and irregular sampling, right? So we integrate them very densely, very accurately, then we just drop some observations randomly, we add some noise on top, and then you just do next token prediction on the known expression, right? So you have your vocabulary for the output of tokens, all the functions, the operators, the symbols, and you just do the standard cross-entropy loss. There's a little subtlety for how you encode numerical values, right? You don't want to have 1 token for each float, so that's something you can play around with a little bit. And here we used some ideas that were somewhere hidden in the appendix of the AlphaGo paper that worked quite well. And then, essentially then it's just a big training task. And of course, if you only have this empirical work, then you have to do extensive comparisons. And this is what we do here, essentially. So take all the known methods for symbolic regression. Yeah, I totally forgot, right? Why would we want to do that? In the neural ODE work, we still only get the system as our neural network, right? If you want to know f, then I can hand you the weights and say, this is the f I've learned. And it's completely uninterpretable. It's really hard to say what the dynamics look like. Very different here, where I literally give out, as a string, the sign of x and so on. So symbolic regression here, there's good reasons to think it's useful. And all of this work has been driven by a PhD student in my group, Sören. And here we evaluated this against all the other methods on different noise levels. We look at how well the methods do. So here NSOD and NSOD-EPS is the noisy and non-noisy versions of our transformer. And they perform on par with the only other method that was designed to do symbolic regression for dynamical systems. All the other methods do symbolic regression, but they were not designed for dynamical systems, but just input-output connections. And they all rely on finite differencing if we want to use them for dynamical system. So they really break down once you have noise and irregular samples because the finite differencing becomes very inaccurate. So it's nice to see that designing something specifically for dynamical systems seems relevant and seems to help. And then the one edge that we still have over this other existing method is that we are way faster in inference time. It's dropping all the training time, obviously, but all the other methods, for each new system, you need to train a separate model. You need to do a separate optimization for this observation. Whereas for us, once the network is trained, it's only a forward pass. Okay, now we're also working currently on a multidimensional extension to this. So I haven't said this, I think. In this previous work, we only did this for scalar autonomous homogeneous systems. Non-linear, but only scalar autonomous homogeneous. And these are the most boring systems ever. I really only learned that while we were writing it. And once you've seen it, it's sort of obvious. But if you have a scalar system, it can't even do oscillations. Right? So you have a derivative function, and you can only get monotonic behavior of the trajectories. So either they diverge to the positive, they diverge to the negative, or they approach a fixed value. They can do slight wiggles on the way to approaching any of those, but they can't ever turn around. So really, it's an extremely limited set of systems. Was still good enough for ICML, luckily. But now we wanted to do the proper thing, which was the goal in the beginning, but we didn't manage. Now also with Stefan, who's doing great work on this. Same idea. We did lots of tweaking and tuning of some of the token representations and tweaking the embeddings and the decoders. So lots of engineering. But same idea. Now you just feed x1, x2, and t. So a multi. You add one dimension for having systems, so multiple variables. Put it into a transformer, use cross entropy loss, and train a big transformer. And now it works pretty well, unexpectedly well, also for higher dimensional systems. So these are some example systems. And while doing this, we also realized that there is not really a good benchmark for this, for symbolic regression of ordinary differential equations. It's relatively niche, I guess. So we also compiled, went through a textbook on dynamical systems, and we sort of manually wrote out all the systems that people have used to actually model a realistic phenomena in different dimensionalities. And there are some chaotic ones, some nice periodic ones, so lots of fun systems in there. So we're also soon going to release that as a benchmark. Not sure how many people are actually in need of such a benchmark, but we definitely needed one. And again, sort of now on this benchmark, the transformer, now we have a better name for it, ODEformer, performs pretty good. There's other methods, this PySAR, which is pretty well optimized, is sort of the go-to implementation of symbolic regression. And if you do that on all the time points, then it works relatively well because it makes use of the finite differencing, right? It sort of tries to learn f as a relation between x and x dot, but you need to provide it with x dot, so you can only estimate it from x. And once you drop some of the points, so once you have irregular samples, then performance really degrades for most of the methods here. And this is where ours still works pretty well. Also across different noise levels, it works relatively robust. The complexity of the equations it gives out is not crazy. Not going to go into the details, but complexity measures sort of how complex, how large is the expression you put out. And many of the evolutionary algorithms that do mutations and permute across operators, they often give out 3 pages of an equation that happens to actually give really good reproduction, but clearly is not a good equation. So this is also a metric that's commonly tracked in symbolic regression, which we also seem to be in line with most methods. And inference time is still pretty good. There's faster methods, but then often they don't perform so well. Okay, now I have a long. Okay, it's 10 past, I think, it's exactly 60 minutes. Long outlook. There's still tons of interesting questions I'm interested in. So theoretical questions still pretty open for what happens in sparse linear systems, but also others. Many questions in the finite sample identifiability, which I haven't really talked about it all. There's some preliminary or initial results again, but not much on what to do if you really have discrete observations in terms of identifiability. If we do believe that identifiability is not achievable, then ideally we shouldn't just output one candidate, but rather a distribution of over functions or give some uncertainty. And especially in the symbolic regression case, I'm not clear how to even express uncertainty around symbolic expressions. Yes, there are useful notions of putting bounds on it, right? I don't know the exact function, but it's between here and there, but then the between is not clear for functions, really. And yeah, there could still be more ideas of incorporating prior knowledge. Right? I've talked a bit about sparsity, a bit about some constraints, but it would be interesting to combine this with a physics-informed neural network approach. We haven't yet made use of the fact that often we may have multiple trajectories from the same system, which should help largely. We tried to do this in the previous work, but the naive things we tried didn't work out at all. And one thing that came up often in discussion with people from both the health and the climate sciences is that often they observe a system where they know the main dynamics. Let's say, for climate, if you want to do large climate model simulations, then for a large part it's Navier-Stokes. But then, of course, there's all kinds of other weird effects, the sun in the atmosphere and what gets absorbed and so on. So we can write out a parametric form for the main part, but then there's also something else that we want to just learn as a neural network. So the first part is parametric, like the SIR model. We are really interested in this 1, 2, 3 parameters, but then there's this other add-on that should just learn all the rest. And clearly, what's usually interesting then is the theta values, right? Like, what are the parameters exactly in the atmosphere? But it's not clear how to train those. Like, in principle, very easy, right? Like, here, just put in the form and learn the thetas, and here, just make it a neural net and learn all the parameters. But the main danger is that G will capture parts of F as well, right? Like, if you have a flexible neural network, why wouldn't it just absorb some of the dynamics in there and just ditch the F altogether? How do you get reliable uncertainty, reliable distributions for thetas if you want to learn these hybrid systems? And one thing that we're also quite invested in at the moment is going back to the sparse case, where ultimately often it's already useful to just look at the input-output connections. And I'm not claiming we can learn the full functional form of a motion capture dynamics of walking, but if I learn relevant input-output connections, that may already be interesting. So the question is, maybe that's simpler, right? If I don't ask to learn the full dynamics and then read off the input-output connections, but can it just directly only learn the input-output connections and let the function be what it is? That may also help identifiability of just the structure and not asking for the full function. And also, yeah, we're slowly making progress on that. And then, of course, there's all kinds of extensions for PDEs, stochastic differential equations, delay differential equations, and all these varieties that you have. OK, thank you. A bit over time.